Okay, good morning, students. As you know, this is Subodh Pandey, and you are floating with me in the world of physics. Okay, so as you know, we are going through a chapter, and the chapter name is surface tension. Okay, so in that topic, or we can say in that chapter, there is another topic, and the topic is surface energy. As I have already told you that as you can see that there are a unique property, and that property occurs due to the non-uniform force experienced by the molecules of the surface of the fluid. So here this is your next topic, and this topic is surface energy. I have already told you that if you know the surface tension, then you can easily calculate the force experienced by the molecules of the upper surface. And you can also calculate the surface energy. Now the question is this: from where this surface energy comes, and how we can generalize the formula for surface energy. So let's get started. As you can see here, it is clear written that a molecule well within the volume of a liquid is surrounded by the similar liquid molecules from all sides, and hence this is no resultant force on it. Okay, this thing I have already explained to you. If you see this molecule, so this molecule is surrounded by the similar molecules like this way. So this molecule you can simply see like this way. So all the molecules are of same fluid. Let's suppose water. So this one molecule is experienced force by this molecule, then this molecule, then this molecule, this molecule, this molecule, this molecule, this molecule, and this molecule. So these molecules are the neighboring molecules, and because they are same in nature, same in configuration, because they all are the part of the same fluids, that's why they will apply the same force. And because they apply the same force, it means the resultant force becomes zero. So I hope that this thing is now clear to once again all of you. Okay, on the other hand, a molecule in the surface is surrounded by similar liquid molecules only on the one side of the surface, while on the other side it may be surrounded by air molecules or the molecules of the vapor of the liquid, etc. So what does it mean? It means if this molecule comes to the surface of the fluid. So let suppose this is the molecule which is at the surface of the fluid. You can see here like this way. Okay, now what? So below it same type of molecules are there, but upper side if we see, then there will be different type of molecules. So the molecules may be of air, may be of vapor, as it is written here. Okay, now this thing is clear. Now what? There is a resultant inward force on the molecule in the surface. Resultant inward force. What does it mean? It means if you have the molecule like this way, the forces are applied by the neighboring molecule, you can simply say, and the molecules of the air also applies force. Then there should be the difference of forces. Let be the force experienced by these molecules be F1, and the force applied by these molecules be F2. Okay, now you can easily realize this, that these molecules are heavier in density with compared to air molecules. So they will apply the more force. It means F2 that will be greater than F1. And these neighboring molecules tries to pull the molecule. Let's suppose this is a molecule, so these neighboring molecules tries to pull the molecule A towards itself. So what this force tries to pull the molecules into the liquid. Okay, it means the molecule which is at the surface move slightly towards the downward direction. Thus, the surface layer remains in microscopic dis microscopic turbulence. It means there will be some hodgepodge conditions will be there, because the molecules of the surface, let's suppose these are the molecules which are resides on the surface of the molecule, so the molecules are pulled by the molecules of the fluid itself, and the motion will be downward. It means we can simply say that the surface will in the condition of a turbulence, means in vibrations, you can simply say. Molecules are pulled back from the surface layer to the bulk, and new molecules from the bulk go to the surface to fill the empty space. It means you can simply say that if these molecules are pulled, then they will come here, let's suppose, and now this surface is totally empty. Now what will happen? Whatever molecules are below from the surface, then these molecules will move and occupies the empty space of the surface. Okay, when a molecule is taken from the inside to the surface layer, work is done against the inward resultant force while moving up in the layer. So it is clear that when I have told you that you have molecules which are on the surface are attracted by the neighboring molecules like this way, then what will happen? These molecules left the surface and move to the deeper side, and the surface becomes empty. Then what will happen? Then again the lower molecules move to the empty surface like this way to fill the empty space of the layer. It means the motion of the neighboring molecule is against the force which is applied by the neighboring molecules. That's why it is written that the work done against the inward resultant force is there. The potential energy is increased due to this work. As we know that you can simply say that work done is the negative of change in potential energy. So if there is a work done which is against the force, it means the change in potential energy increases. A molecule in the surface has greater potential energy than a molecule well inside the liquid. It means as we have told you that potential energy increases. It means simply we can say that the molecule which are at the surface of the fluid having higher potential energy. It means if this is surface, this is molecule on the surface, this is molecule in the deeper side, this have potential energy U1, this has potential energy U2, so U1 must be greater than U2. Okay, the extra energy that a surface layer has, it called the surface energy. So whatever the extra energy means, because these two molecules are basically of the same fluid, it means they must be possess the same energy. Okay, but here you can see that u1 is greater and u2 is smaller. U1 is greater because uh, it is the work done which is against the force, though, so it must be greater. Okay, so if we calculate the difference, means u1 is greater and u2 is smaller, so u1 minus u2, that will be your surface energy. Okay, now what? The surface energy is related to the surface tension. So this thing I have already told you, that if you know the surface tension, then you can easily calculate the force experienced by the molecules on the surface of the fluid, as well as you can calculate the surface energy, means how much work is done against the force to pull the deeper molecules to the surface of the fluid. So let's get started with an experiment. As you can see, consider a U-shaped frame with a sliding wire on its side. So this is your U-shaped frame, this is U-shaped, and this is your wire, sliding wire. Okay, suppose it is dipped in a soap solution. So now we dip it, take out, and placed in a horizontal position. The soap film that is formed may look quite thin, but on the molecular scale, its thickness is not small. It may have several hundred thousand molecular layers. So it has two surfaces, including a bulk of soap solution. So this thing I have already explained you in the previous lecture, that if we take a normal water, then it have only one layer, or due to one layer it have only one surface. But in case of soap solution, we have dual layer, or we can say we have dual surface area. Okay, both the surfaces are in contact with the sliding wire and hence exert forces of the surface tension on it. Because I have told you that surface tension S, that is force per unit length, and if the length is twice, means there are two layers, so definitely the force will be affected, because F will be S into 2L. So in place of L we have to put the 2L. Okay, now what? If S be the surface tension, so solution, L be the length of the sliding wire, each surface pull the wire parallel to itself with a force SL. The net force of pull of the wire due to both the surfaces, F equal to SL, or you can say F equal S into 2L. So this thing I have already explained to you. One has to apply an external force equal and opposite to F so as to keep the wire in equilibrium. So it means because F force is applied by the surface of the soap solution. So you can see that this represent, we can say this is the technique to represent the double surface. Okay, so two arrows are there. So this is 2SL force which is applied by the surface of the fluid. Now if we apply same amount of force but in the opposite direction, then what will happen? If this condition satisfy that F is equal to S into 2L, now this F is becomes external F. Okay, firstly that F was the internal F, or F of the surface. Let me explain here. uh, it is firstly it is the force due to surface tension, or we can say that the force due to surface itself and due to surface tension. Now if the force which is due to surface tension is equal to F external, then the sliding wire will be in its equilibrium position, means it will not be in motion. Okay, now what? Now suppose the wire is slowly pulled out by external force. So as we have discussed here that the force F, whatever is external force we have applied here, that is equal to the force which is due to surface tension. And in this equation, the sliding wire is at its equilibrium position. Now if we increase the external force, then what will happen? Then we can simply say that the wire will be slowly pulled out. Okay, and it covers a slight distance x. So the area of the frame is increased by L into x. Okay, so because we know that area, that is length into width, and width is taken as x. X is what? X is the displacement. So you can see here, let's suppose when we increase the force, then this is your increase in width x. Okay, so we have twice area, so 2a, and 2a will be 2lx. Now what? The liquid from the inside is brought to create the new surface. Okay, the work done by the external force in the displacement. Work done, we know that force into displacement. Now force is what? Force is 2SL, as I have already explained to you. That is force, that is 2SL, this one. Okay, so here 2SL and the displacement x, so it will be s into 2lx. Okay, now you can simply say that this work is nothing but the potential energy, it means U. So it will be U, that will be equal to W, or we can say the work done. So it will be S into 2Lx. Now 2Lx is what you can see here. 2Lx is nothing but 2A. Okay, so in place of 2Lx we can place A. So you have a formula that is U upon A, that is capital S. So here you can see that if we know the surface tension and the area, obvious, if we know the surface tension and the area, then we can calculate the surface energy. Or if we know the force, if we know the surface tension and the length, then we can calculate the force. So it is the unit thing you should remember. Okay, we see that the surface tension of a liquid is equal to the surface energy per unit surface area. In this interpretation, the SI unit of surface tension may be written as joule per meter square. It may be verified that Newton meter inverse is equivalent to joule meter inverse 2, and this is same process which you can go through by your dimensional analysis. You can convert one system of unit into another system of unit, or you can check that unit is correct or incorrect. You can check whether the formula is correct or incorrect. Yeah. So by uh, using dimensional method, you can easily check that Newton meter inverse is equivalent to joule meter inverse 2. Okay, I hope and I believe that this thing is now clear to all of you. Okay, so this is your example, as you can see here, and it is given that a water drop of radius 10 to the power minus 2 meter is broken into 1000 equal droplets. So we have one drop. Let's suppose this is your drop, and it is distributed like this way into 1000 droplets. Now what? Calculate the gain in surface energy. Surface tension is given to you. So as I have told you that if you know the surface tension and the surface area, then you can easily calculate the surface energy. And the formula is, as you can see here, the formula is U upon A, that is S. So uh, U upon A, and that is S. Or you can say that U equal S into capital A. S here surface tension. Now if we talk about this area, so as we know that the drop is basically in the shape of the sphere, so the area can be taken as 4 pi r square. Now this thing is now clear to all of you. This is the basic formula which we are going to use to solve this question. If we think about it, then it is given that the radius capital R means the radius of the big drop, and that is 10 to the power minus 2 meter, and we don't know the radius of the smaller drop. So firstly, how we can calculate, because we are in need of 4 pi r square like this. So until we don't know the value of small r, then how we can calculate the capital U or the energy of the small drops? So firstly, we have to calculate the value of small r. How we can calculate? The question is so simple. We can calculate by using the concept of constant volume, because the big drop is converted into 1000 droplets. It means the volume must be same. And if the volume is same, then what we can write? We can write that volume of bigger drop, volume of bigger drop must be equal to volume of smaller drop. Okay, so volume of bigger drop, that is you can say 4 by 3 pi r cube. This is capital R. And here volume of a smaller drop, it means 1000. There are 1000 droplets. A small drop or droplets. Clear? So small droplets. 1000 into 4 by 3 pi is small r. Now what? As you can simply see that now we can 4 by 3 pi cancelled out, and we have capital R cube, that is 1000 small r cube, or capital R equal 10 small r. So this is the relation between capital R and small r. Means if we are in need of small r, then we can place the value of small r in terms of capital R, or if we are in need of capital R, then we can place the value of capital R in place of small r. So you can simply write that small r equal nothing but capital R by 10. Now by using the same formula, this formula U, so this formula, if we again write, then you can write that capital U, and that is for small droplets. That is what? That is capital S into, this is for one drop only. Okay, so that's why I have written here one drop. So capital S into 4 pi small r square. Okay, so this is your capital S into, firstly we take the complete potential energy. So this is, let's suppose, potential energy of small droplets. So if it is a small droplet, then it will be S into 1000, 1000 times 4 pi small r square. Okay, so it will be capital S into 1000 times 4 pi, and in place of small r you can place capital R by 10, so this will be of square. Now what? As you can see here that it is capital S into 1000 into 4 pi capital R square by 10, so it can be written as potential energy of smaller droplets, that will be capital S into 1000 into capital R square upon 100. Okay, so you can see that now two zeros here cancelled out, and we have simply that small droplets have the energy that is 10 times capital S capital R square. So this is your equation number first, that is for bigger drop. Okay, and this is your equation number 2, that is for the small droplets. So delta u you can simply write down that that will be equal to potential energy of small droplets and minus something is missing there, I think. Yes, 4 pi is missing there, so 4 pi will be here, so it will be 4 pi. So small droplets minus the energy of the bigger drop, so that is 10 times 4 pi r square s minus, and the bigger drop is your 4 pi r square into s. So 4 pi r square into s. So it is nothing but 10 minus 1, that is 9 times. So 4 pi r square s. That is delta u, or we can say that the change in potential energy. So it will be 9, 4 pi, you can write 3.14 into capital R. So capital R is given to you, that is where is this one, 10 to the power minus 2. So it is 10 to the power minus 2 and the square of it, so square into and capital S. Capital is 0.075, so it is 0.075. Now we have to solve it. So 9 into 4, so it will be 36 into 3.14 into this will be minus 2 power minus 2, so it will be minus 4 and 0.075. Now what, we have to multiply it simply. So now we will take the help of the calculator. Okay, so as you can see that it is written that 36 and multiply by 3.14, and then it again multiply by 0.075. So finally it comes 8.5 into 10 to power minus 4 joule, because it is energy. So this is your final answer, and I hope, I believe that this theory is now clear to all of you. In the next topic, we will, as I have promised to you, that we will show you each and every derivation in the detailed manner. So this is your next topic, that is the excess pressure inside a drop. In that lecture, we will discuss that how we can calculate the excess pressure. Okay, so for this lecture, this is all, and thanks for watching, thanks for listening, and please try to this numerical by yourself. Thanks, best of luck to all.